Good evening, everyone. Welcome to the fourth tutorial session of the online tutorial session of the NPTEL course, Physical and Electrochemical Characterization Techniques. So, yeah, as I said, so let us start our class. So, as I said, this is our fourth week, and we have covered a little bit, and we have so in this course we basically deals with the physical and the electrochemical characterization techniques that are used in the chemical engineering. So, as I used to tell on every classes, these techniques are not only just limited to the chemical engineering, but this has a wide use in all the fields of science where people actually deal with materials. So this has these tools are in hand for the departments, for the researchers from the Department of Material Science, people who do research in physics, in physics people who do research. Like there are many groups across India who works on batteries and sensors. So these people would regularly deal with these kinds of characterization and electrochemical techniques. And people from the chemistry background, chemical engineering background, chemical engineering background, or people even from the biotech background, etc. These people would be regularly using these kinds of experimental techniques. So So yeah, as I so this is course is run by Professor uh, Professor Tamal Banerjee, Professor Tamal from IIT Guwahati. So hope you have listened to all the three previous week lectures, and the starting from the first lecture, which give us introduction on what are the uh, basic characterization techniques that we may like we will be discussing in this course. And the second thing we basically discussed on the infrared IR spectroscopy and FTIR interests. Then we discussed Raman spectroscopy in the previous class, and now in this we are moving away from this um, spectroscopic techniques to some other physical techniques, which is basically where we measure the surface area and pore size of the different materials. So this is a very efficient and a very necessary kind of study where people actually deal with materials and whose surface properties depends heavily on their research. For example, if people are working on batteries or sensors, then surface area plays a key role in the performances. The material which has a very high perform specific area can give a better performance in this area. So people always tend to go for materials that can give a higher specific area. Specific area is the area per gram of material. So if you take 1 gram of material and if you place it one after another, like what is the area that you can cover? So that is the basic idea where we will talk about specific area. So so these things are very important for the people from the background of all this. So now myself, I'm Rahul. I'm a primary research member from the Department of Physics, IIT Kharagpur. So I have been handling this course for last 3 weeks, and I'll be handling this course, this online tutorial session, for the next coming weeks. This is the 8-week course lecture course. So in the upcoming weeks also, I'll be handling these kinds of sessions. And if you have any doubt, you can contact me on my mail ID, which I'll be writing here. Rahul, RIDIN. C96 at gmail.com. So if you have any doubt regarding this, you can directly write to me in this mail ID, or these things will be uploaded in the YouTube channel, so you can get the information from there also. So now let us start the session. Let us do not waste any much more time. So the first question for today. So basically in this session, I will be reading you out the question. I will be just explaining you the question. Then I will give you a few minutes for you guys to think over the question because it's not a one-way class where I just talk and the students just listen to whatever the teacher say, but the student have to think for themselves and try to come up with the answer, and then we'll discuss that answer in much more detail. So yeah, as I said, this is the first question. So let us identify what are these A, B, and C. This is a very primary figure that Professor Tamal has explained in this lecture, and it has a very great important once we are dealing with the experimental nano. So what are these three different parts as shown in the figure? What is this A? What is this B? And what is this C? I can give you a few seconds for you guys to think the answer. If you guys could come up with the answer, that's very better. Or else I will explain you what are these within a few seconds. So take a few seconds, think about the answer. The question was identify A, B, and C. So what are these different structures as shown in the figure? What is this A? What is this B? And what is this C? So just think about for a few more seconds, then I can tell you the answer. So these are very basic and preliminary things. So we need to get an idea on what are these, unless we proceed to further more technical terms. So these are very fundamental things. I think these should be, so students should be aware of these things. That's why this came to be the first question. And I think you guys got enough time to think about the answer. Our answer to this question is, yeah, just a second. So to this question E, the A stands for mesopore. A comes to mesopore, and B corresponds to the micropore. So these are the three things that is basically happening here. So the A is basically the mesopore. Mesopore is a kind of pore with its pore value in the range of some that we will be discussing when next question. And the micropore is something uh, is another length scale of the pore. So yeah, suppose you have a material, say, just a second. Yeah, suppose we have a material. Suppose this is a material, but always these material we having some kind of force within itself. So there will be enough plenty of force within inside. So these force will actually contribute to performance boost, or that depends on the application. So depending on the application, this force size can give a cutter, or that can alter the performance of the your total device. So you need to know exactly what is this pore size, and you can say that this particular reason for this kind of a behavior of this kind of a material may be due to this kind of process, because the material is having a mesopore or economical pore. So this is a uh, very important thing that we need to be aware of. So these things are the basic things that people will measure when they're doing a surface area and pore size measure. One of the basic things. So they will measure other kinds of parameters. So these are the few parameters that people generally measure. Now let us go to the next question. I hope this is clear for you. Now let us go to the next question. So the next question is, what are the basic properties that are generally measured using this option? So yeah, So basically the absorption like the once we are having absorption and there is this absorption. Absorption is Absorption is when something is pulled directly into the material. Well, absorption is a surface property, because things are not going inside, like things are just residing on the surface. So there are basically two kinds of absorption. One is the physics option, another is the chemisoption. So we will be discussing more about this. So the first category of this absorption is physics option, and the question is what are the general properties that will be measured in the physics option. So I can give you a few seconds to think about the answer. Just think if you can figure it out. So these ideas has already been discussed in the class by Professor Tamal. So just think about the answer. Just revise your memory. Try if it is possible for you to get the answer. Second, read the question once again. What are the basic properties that are generally measured using physics option? Just think for a few seconds, and you need to know the answer. Sorry. Yeah. So the question was, what are the basic properties that are generally measured using the species of it? I think you got enough time to think about the answer. So the answer to the question is surface area. First thing that people generally measure is the surface area of the material, the pore size of the material, the pore width of the material, and the fifth one is the other prominent properties. So basically, let us stick to these three. So these three are the primary things that people measure while doing a physics option technique. So basically, first one is the surface area, pore size, pore width. So you have a material. Is a material, and so this is just a flake of material because yeah, this is a very let us go to this the scale is very small. So yeah, the square is very small. So in this, what is this area? So is a dimensional object. So it has all areas in surface. So what is this area? Basically, this area is generally known as the specific area. Specific, okay. Yeah, basically this area is the specific area which is generally represented in the units of meter square per gram. So this is kind of an area. But you see here is a very different unit for this system. So means that you take a material. So like there is a material here. Yeah. So this is your container, and this is your material here. you take 1 gram of this material and you started arranging them in this manner. The contents in that material, you started arranging this one after other. You construct your spherical force and you arrange that. And what is this? What is this area? Area, that area you cover, that you can cover with this much amount of material. So that is basically what specific area denotes. Okay, then comes the pore size. So the material will be having different pore. What is the size of that pore? So like it will be like tunnels inside the material. So yeah, what is that the size of that pore? And what is that volume? So is that a very deep, shallow, or is that a deep pore? So pore, that all depends. So the basic factors that are measured, the basic properties that are generally measured are the surface area, pore size, and pore volume. Now let us go to the next question. I hope this is very clear to you. So let us move on to the next question. So the next question is, micropores are in the range of dash. So yeah, as I told you, there are micropores, mesopore, and yeah, 3 types of pore. So what is the range of micropore? Micropore, mesopore, and macropore. So here we have majorly we are having these three. So let us go one by one. What is the range of micropores? So I can give you a few seconds to think about the answer. Like I don't want to do the answer right away because you have to think what you have been learning in the class. So that is the main thing about the tutor interactive tutorial. It is basically interaction. So if you have any doubts or you have any doubts regarding the question, you can directly ask me. So I'm giving you the time for all these concepts. So let's go for a discussion. So yeah, let me know what are your doubts and your ideas regarding this question, which is the micropores are in the range of dash. So what is this range of micropores? So from which length scale to which length scale do we generally call the as micropores? Yeah, I think you guys got enough time to think about the answer. So the answer to this question is less than 2 nanometers. Yeah, less than 2 nanometers. So this means that if the size of the core is less then 2 nanometer. You call it as micro ohms. Okay, so yeah, this is a very easy question. Now let's move on to the next question. Yeah, so the average sizes is that 2 nanometer. So that's that. That's what you can see. Yeah, all right, go to the next question. So mesopause are the range of dash. Yeah, you talk about initially talk about micropore. Now let's talk about mesopore. So what is the range of mesopore? Just think about the answer. If you have any doubts, just discuss with me. I'll be here to answer your questions. And yeah, what is the range of mesopores? Yeah, I think you guys got enough time to think on the answer. So the answer to this question is mesopores are those horizontally the two sizes, which is around 2 to 50 nanometers. So if you're having a pore and the size of the pore, you have a material center and this having a pore, and the size of this pore is in the range 2 to 50 nanometer, then it is called the mesopore. So this is the answer. So I think we're able to get the answer. Now let's go to the third question, which is what is the size of macro? So this is very fundamental things. Just think about this question. What are the size of a macro? So I'll give you a few seconds to think about the answer, then we'll discuss the answer with you. I think you guys were able to get enough time to think about the answer. The answer to this question is about just a second, I can put this. This question is about 50 meter. Yeah. So now just discuss one second. So now we are having pores. The pores are what basically three types. One was micropore. The other one was mesopore. Other one is macropore. So we saw that the micropores are in the are of the size less than 2 nanometer, and we saw the mesopores are generally in the range as taken to be in the range of 2 to 50 nanometer, and the macropores are taken in the region above 50 nanometer. So this is a very fundamental classification of the force that people regularly use. So this is a very important parameters that one need to remember. Now let us go to the next question. I hope this much is very clear to you. So let's move on to the next question. Yeah, as the answer is micropores are the size above 15 nanometer. Now the porous material, yeah, have the advantage of dash, which lead to dash performance. So this is actually it's not the porous. The porous materials, the porous materials have the advantage of dash, which leads to dash performance. I've already given you the answer, but think about this answer. So if you really remember what we have started discussing with, then this question is very easier for you. So I'll read the question once again. The porous materials have the advantage of dash, which leads to dash performance. So just think about the answer for a while. Then I can tell you that. So I think you guys don't have time to think about that. So the porous materials have the advantage of dash, which leads to dash performance. So the answer to this question is the porous materials generally have an advantage of higher surface area. So we have already discussed this higher surface area, and this leads to, yeah, as I also, this leads to higher performance. So the answer to this question is that the porous materials generally have the advantage of higher surface area, which leads to a higher performance. It can be a performance in charge discharge, in basically charge storage, or maybe in sensing, or maybe as a catalyst, etc. So this has, etc. There are many examples, and mostly in all these cases, this higher surface area can lead to very higher performance. Yeah. So yeah, this answer the higher surface area for higher reactivity and higher performance. So let's move on to the next question, the question number 7. Here the question is the dash and dash determines the internal surface area. So this is a very crucial question. So I think you may be able to find out. So it's not that difficult, but this is somewhat important. So the dash and dash determines the internal surface area of a material. So if you have a material and if you have the idea about these two parameters, then you can determine the internal surface area. So what are these? I can give you a few seconds for you to think about that, sir. If you have any doubts or you have any ideas, just come and discuss it with me. So I'll be here. I'm just giving you a few seconds for you guys to think about the answer. Yeah. So the answer to this question is, so I got you got enough time to think about the answer. So the answer to this question is size distribution, size distribution, and the number of pores. So these two are the main two factors that determines the internal surface area of material. First one is size distribution particle, and next one is the number of pores in the structure. So I hope this question is clear to you. And so let us do not waste the time. Let's go to the next question. Just yeah, the answer to this question is size distribution and number of pores. Okay, so now let us move on to the next question. The next question is the formation of pores is usually initiated during the dash process. Formation of pores is usually initiated during the dash process. So again, I can give you a few seconds to think about the answer, then I will let you know the answer. Can you read the question once again? Formation of pores is usually initiated during the dash process. So during which time? So like is it during the yeah, which the rest of the questions this part of the experimental process where you deal with the formation of pores. So thinking about a few seconds, then I'm definitely to do the answer. Yeah, now I think you guys got enough time to think about the answer. So The answer to that question is it is yeah. So the formation of pores is generally initiated during the preparation process of the material. Preparation process of the material. So it is during that time when this pores generally start occurring in the material. Yeah. So now let us go to the next question, which is dash force is responsible for surface absorption. So now we have a material and we have absorbed it. For this thing to absorb into the surface of the material, you need to have some kind of force. So what is that force? It's electrostatic force, it's electromagnetic force, like yeah, it's a magnetic force, or is it kind of something like that force, or it's a gravitational force? Yeah, there are different kinds of force. And which one do you think which is responsible for absorption of the particles within the material? So I can give you a few seconds to think about the answer, then I'll discuss the answer. I can read you the question once again. Dash force is responsible for the surface absorption. So I think you got enough time to discuss and think about the answer. So the answer to this question is van der Waals force. Answer to this question is van der Waals force. So the van der Waals force basically plays a crucial role in determining the surface absorption properties of different material. So if the van der Waals force is higher for some material and for the absorbent and absorbate, then the absorption will be much more higher. And if that van der Waals force between the absorbent and absorbate are lesser, then the area of absorption is lesser. So the answer to this question is certainly it is such. And the dash case is generally used in business object. So we say oxygen, then hydrogen, or they say helium. So yeah, you can think of any other. Or is it water vapor? Yes, let's go to one of the yeah, which one of the above is hydrogen? I mean, which one of this above is generally used in physics absorption? So I can give you a few seconds to think about the answer. Then I will explain the answer to you. So yeah, the question was dash gas is generally used in physics option. The options that I gave you was oxygen, nitrogen, hydrogen, or none of the above. So generally the gas that is used in this kinds of techniques are nitrogen gas. Okay, so we got the answer. Now let us move on to the next question. The next question is, what are the basic two classification? But so I've already told you the answer, so just think about for a while, then I'm going to give the answer. I think you guys got enough time to think about the answer. The basic two classifications of absorption are, yeah, absorption are this, is sorption, the other one is sorption. So this is surface property, and here there is actually a bone formation on the associated with. So these are the basic two classification of absorption that are generally observed. Now let us move on to the next question. Next question is, yeah, versus option. You can see the answer. Versus option and finish option. The next question is, van der Waals force consists van der Waals is mainly due to the dash and dash of the molecules. So what are the two basic parameters that van der Waals force basically depends on? So just think about the answer, then I will give you the answer within a few seconds. Yeah, so the question once again I want to review is the van der Waals forces consists is mainly due to like what are the major factors. So this question can be rephrased as on what parameters does the van der Waals force depends upon. Yeah, just for a while, then we put in our answer. I think you guys got enough time to think about the answer. The other question we can read the question once again. The van der Waals force consists mainly due to the dash and dash of the molecules. What are the two parameters of the molecules that mainly dominates or that mainly controls van der Waals forces? So the answer to this question is the shape and the size of the molecule. Shape and size of the molecule. So these are the two parameters that basically drives the one of us to be that certain, and that's a bit of a assumption. Van der Waals force is basically to the shape and size of the cubes. Okay, so if you're fine with this question, now let us move to the next question, which is our 13th question of today's session. And the question is, NFS option process. The energy release are quantified with. So in what form does the energy gets released during the physics process? So yeah, so when an molecule just come and sits on the surface of another molecule, there is some kind of energy difference that's happening, and this energy difference is being supplied out to the environment in some kind of form. Is it in the form of light? Is it in the form of heat? Or is it in the form of vibrations? Or is it in the form of sound? So which of the following can be uh, the way in which the energy that usually released during the physics process? So just think it for a while, then I will look at the answer. I think you guys got enough time to think about that. So yeah, in what form does the physics option process generally releases the energies in the form of heat, light, sound, or vibrations? So yeah, the answer to this question is roughly the heat. So in the physics option process, the energy is released in the form of heat. So I think you guys got the answer. Now let's move on to the next question, which is briefly explain the process happening in the chemistry. So briefly explain how this chemistry process happens in the material. Okay, so this is a briefly more intuitive, not just intuitive, you need to know how this process really happens. So yes, just as you should just think for a while, or if you have any doubts, just discuss with me. Even with any previous question also, just we can always go back to that question and then discuss. So just keep it a good conversation and we can then make it a more interesting class. So yeah, now just briefly explain the process happening during a consumption process. Yeah, think it for a while, then I'll let you know the answer. Yeah. Now let's discuss the answer with you. So, explain the process in so, answer to this question is as the temperature rises, the absorbed the rearrange themselves the surface. The first thing that happens during absorption process is that as the temperature rises in the absorption process, the absorbed molecules will get rearranged themselves. So if it is initially in some kind of ordering, that ordering changes altogether, and now they rearrange themselves into a new kind of ordering, and this new kind of ordering is electronically like it's basically an electronic reordering, and this ordering is with to the surface molecules. And the electronic rearrangement also causes breaking and formation of new bonds. So basically, this can be uh, like if there is some existing bonds, and during chemisorption bonds, that existing bonds can either break or they can also form a new bonds with some new other. So the basic two things that will be happening in chemisorption process is that it will happen a electronic rearrangement of atoms, and this electronic rearrangement can be like breaking of bonds or formation of new bonds. So this is one thing that you have to keep in your mind very specifically, that in chemisorption there is breaking and formation of new bonds. Okay, so if it is very clear to you, then let's move on to the next question. The next question is identify the two processes. Process A, what is this process that you have seen in process A, and what is this process A, what is this process B? So identify these two. I can give you a full. So in this, the van der Waals, there is this van der Waals force and this collision bond formation. So what are these two processes? So just take a while to identify them. And if you're having any answer, just talk to me. Just discuss it with me. And if you have any doubts, just ask me. Okay. So I'll give you a few seconds to think about the answer, then I will get back to you. I think you guys got enough time to think about the answer. So the question was identify this two process, and there is a clue over here. The first one has van der Waals force associated with it, and the second one has chemical bond formation associated with it. So the answer to the question is the first one corresponds to physics option, and the second one corresponds to chemistry option. So as we have already seen in the previous questions, and physics option van der Waals force plays a van der Waals forces plays a crucial role, and in case of chemical bond formation. In case of chemistry option, chemical bond formation, which can also be chemical bond breaking, and this plays a very crucial role. Now, yeah, here the answer is already given. So now, so this is also good because this is a very deep question, like it has many parts associated with. So now this question is like give a brief comparison between chemistry option and physics option process. So what are they? So now let's discuss it one by one. So in phases of report, the enthalpy changes, which is basically delta U, associated with them are very small, that is in the range of 10 kilojoule to 40 kilojoule per mole. Whereas in chemisorption, this is a very high. You can see like it is a 10 times higher values, like it is from 100 to 400 kilojoule per mole. Okay, so yeah, the enthalpy change in the physics option is very small compared to that of the chemical option process. Now, when you talk about to this physics option, it decreases with increase in temperature and increases with increase in pressure. So when the pressure temperature is higher, the particles themselves will get higher kinetic energy, and they tends to move away from the surface and they just go some random paths. And when you increase this pressure, actually the number of particles that are actually coming towards the surface increases, and that will eventually increase the physisorption. Whereas in chemisorption, it involves the bond formation and needs higher energy and takes place at higher temperature. So yeah, that is very clear. That's a very clear sentence. So as we have discussed in chemisorption, it involves the bond formation, and it requires a higher energy to form these bonds, and the higher energy is usually obtained from heat, and thus a higher temperature provides higher energy to the system, and higher energy result in a better bond breaking and formation. So basically in the physisorption process, it basically decreases with increase in temperature, whereas in the chemisorption process, it increases with increase in temperature. One decreases with temperature, the other increases with temperature. The physics option is a multi-layer observation. For example, if you have a layer, and here one, as we have discussed, the van der Waals plays a crucial role. So the van der Waals between the surface and the material, once between these two will form a single layer, and over above this layer can also form the layers, which also depends on this van der Waals forces. Whereas in Kinney's option, it is a very surface to the molecule. Like this is a very particle, and it depends on the particles basically. So once this once a layer of uh, particles are formed above this material, then the further molecule coming cannot directly interact with the surface, and therefore it does not want to form any kinds of layer. So basically, in the physics option, multi-layers are allowed, or it is seen, or it is possible, whereas in the chemistry option, only monolayer formation is possible. And the other difference between physics option and chemistry option is a physics option process is highly reversible compared to a chemical process. Chemical option, which is a very highly reversible, because in physics option it is just kind of a surface property where the particles are coming. Where the particles, like, the say the gaseous particles are coming near the surface and it forms third layer, and it does not involve any kind of chemical reactions happening. Whereas in chemistry, it actually depends on the chemical reaction where there are bond formation and bond breaking, and that this process can be reversible. So once the bond has been broken or when the bond is formed, it is difficult to reverse that process. So basically, a physics option process is highly reversible, whereas a chemistry option process is highly irreversible. Now, physics major applications of physics option. So the preventing process is defining the total surface area for volume forces distribution of the adsorbents for various catalysis. So yeah, that are the basic use of this physics option, which was basically the total surface area to calculate the total surface area, pore volume, and pore size. Whereas chemical option is used to estimate the area of catalytically active sites and their dispersion. So what we need to know how to actually the surface of a material is to some specific gas or something. We can do it in absorption analysis, and you can see that how much area of the your material is actually chemically active and how they are dispersed within the. So the major differences comes from the enthalpy. So it's in the test. revise this question. So the major differences that one can see from this solution and a solution is that first comes from the enthalpy. The enthalpy of this solution is much lesser than and compared to that of a King's option, and the rate of this option increases it decreases with increase in temperature, whereas the rate of King's option increases with the increase of temperature. In form, physics option multi-layer formation is only possible, whereas in chemistry option, it can happen like the monolayer formation can also happen. Now, a physics option process is a very highly irreversible process, whereas the chemistry option process is a very highly irreversible process. Now, the absorption process can generally be used to study the Fountain surface area, the volume, and the pole size distribution of the adsorbate for various catalysts. And the absorption process, which is basically used to determine the effective area, which is catalytically active, and their dispersion within the material. Now let us move on to the next question. I hope this one is very clear to you. So this has a huge implication because we are discussing very large number of ideas over here. So let us move to the next question. The distribution of the adsorbate molecule depends on. Okay, I can read the question once again. What are the parameters to which the distribution of adsorbate molecules actually depends on? I'll give you a few seconds, then I will discuss answer. Yeah, just stay there for a while. Can read the question once again. The distribution of adsorbate molecules really depends upon what parameters. So just think it for a while, then I will do that. So the question was distribution of the adsorbate molecules basically depend on dash. So let us discuss the answer. The answer to this question is the distribution depends upon the pressure, temperature, nature of adsorbate, pore size, nature of adsorbate. Yeah, let us discuss one by one. The distribution of adsorbate basically depends on the pressure. First one is pressure. So as the pressure increases or decreases, it definitely alter the way in which the molecules are absorbed into the surface. Because as the pressure increases, which is basically the number of molecules that are actually coming and interacting to the surface, that increases. So when the number of particles that interact with the surface increases, then it's higher chance that these particles actually get absorbed into the surface. So as the pressure increases, the as the pressure increases, the adsorbent, like the distribution of the adsorbent molecules, will also get altered. The next one is the temperature. So as the temperature increases or decreases, it will also alter the way in which the adsorbent molecules are get distributed within the surface. It is because if you consider the chemisoption process, you need to have a higher temperature to get the bond breaking and all this thing. So, and when you come to the physics option, as the temperature increases, the particles get enough kinetic energy and they will move away from the van der Waals uh, forces, and that can lead to lesser absorption. So, so therefore, the distribution of the adsorption molecules generally depends on the temperature also. Then the nature of adsorbent. Nature of adsorbents. So when the adsorbent changes, it depends. Yeah, definitely. It depends if you have a material and say some particle A is coming to the system, and suppose some other particle B. Now suppose it is coming to this material. So the rate at which these two get adsorbed will also differ because these two are having different kinds of properties. So the distribution differ when the adsorbate actually changes. The next one is the pore size. So if we have an uneven surface, something which is like this, this is a surface of the surface at which things get absorbed. So here you can see that the way in which the particles get arranged or distributed will also changes. Now, if you just take a smaller area, take this area and similarly this area, you can see depending upon the way of this pore, the number of molecules that get actually absorbed into the surface will also changes. So the next thing is the nature of adsorbate. Okay, that we already talked. That now we discussed was process, and the last one is the nature of adsorbing. So which material actually adsorbs the material will also depends the way at which the distribution of the adsorbent molecule depend. So the adsorbate and adsorbent. So basically, adsorbate is the one that actually absorbs something, and adsorbent is something that actually get absorbed. So these two also will play a crucial role in determining the distribution of the adsorbent molecules on the surface. Okay. So I can let you know the answer once again. The distribution of the adsorbent molecule depends on the pressure, temperature, rates of adsorbate, or area, and the nature of adsorbent. So I hope this question is clear to you. Now let's move on to the next question, which is molecules being adsorbed on a solid surface as a function of equilibrium pressure and temperature are called dash. The molecules being adsorbed on a solid surface as a function of equilibrium pressure and temperature is called. So what is basically this process called? Think it for a while, then I will let you know the answer. Yeah, let me read the question once again. The molecules being adsorbed on the solid surface as a function of equilibrium pressure and temperature are called dash. So yeah, let's discuss the answer. So the answer to this question is Absorption isotherms. Absorption. So when you represent the molecules absorption in terms of pressure and temperature, pressure and temperature, then this is called isotope. So basically, you measure pressure. ISO, the temperature, this ISO means constant. So you keep the temperature to be constant at a very lower value, and then you measure the P by P0. So you may get some curves, something like this or something. We will be discussing more about this in future. So these are called the absorption isotherms. So what are these terms? I mean, this is a plural. So these are terms. So let us discuss what are these using the further slides. Yeah. So as I told you, it's not isotherm, it's actually isotherm. So there are different kinds of isotherms. So which is basically denoted as type 1, type 1, type 2, type 3, type 4, and type 5. So identify. So what is this A corresponds to? Is it a type 1? Is it a type 2? Is it a type 3? Or is it a type 4? So you have A, B, C, D, and E, and you're having type 1, type 2, type 3, type 4, type 5. So just this is just like a match the following. Just try to answer which one is a type 1 isotherm, which one is a type 2 isotherm, which one is a type 3 isotherm, which one is a type 4 isotherm, or which one is a type 5 isotherm. Just take it for a while and we'll do the answer. Just think of it for a while. This is a kind of a tricky question. We may need more time. So what are these associated? What does A corresponds to? Is the type 1 isotherm, is the type 2 isotherm, is the type 3 isotherm, it's the type 4 or type 5. Similarly, what are these for B, C, D, and E? Just think this for a while and I'll let you know the answer. Okay, now let us discuss the next one. So the answer to this question is A represent type 5. So this kind of a behavior where there is a very slow increase, like it's kind of a very slow increase, and then it increases at a higher rate, then it saturates. So this kind of behavior This usually goes for the type 5 isosynthesis. Type 5 isosynthesis. And B, you can actually see their increase. It increases even nanover. Then there's a very certain increase. So this kind of a behavior you should observe for type 3 isotherm. And the next one, there's a certain increase, like an exponential increase, then it's gradually slows down. Then again, it increases drastically. So it's like a case written in a mirror way. So this kind of a behavior corresponds to type 2 isotherm. And the D, where you can see there is a certain increase in the sudden increase, then like it actually tend to saturate, and then there's a very slight increase. So this kind of behavior would represent type 1. This kind of a behavior corresponds to type 1 isotherm. And in E, which is a very big mixture, so it actually increases, then it just drops down, then it increases very drastically, then it kind of saturates. So this corresponds to type 4 isotherm. Okay, so I think you got the answer. The first one, A corresponds to type 5, B corresponds to type 3, C corresponds to type 2, D corresponds to type 1, and E corresponds to type 4 isotherm. Okay, so now let us move on to the next question, which is dash isotherm for materials having small pores or micropores and so on. So which is basically the isotherm that is observed for the materials that have a very small pores and or even micropores. That's all. So which is that kind of isotherm? Just think it for a while, then I'll let you know the answer. Plus, let me read the question once again. Dash is the isotherm for dash is the isotherm for materials. Dash is the isotherm for the materials having small pores and micropore absorber. So just think it for one more few more seconds and you have to answer. I think we got enough time to think about the answer. So the answer to this question is type 1 isotherm. So the type 1 isotherm is simply generally associated with the materials that are having very small pores or microabsorbers. So now let's move to the expression. That's why germs are observed for absorbers that are not porous or having higher number of pores and exhibit unimpeded monolayer or multilayer adsorption. So I'll read the question once again. Dash isotherms are observed for absorbers that are not porous or having higher number of pores and exhibit unimpeded uh, unimpeded monolayer multilayer adsorption. Just think for a while and let you know the answer. I think you guys got enough time to think about the answer. So the answer to this question is basically type 2 and type 4 isotope. Answer this question is basically type 2 and type 4 isotope. Now let us move on to the next question, which is which of the following isotope will be observed a quick rise in the absorption volume initially at lower relative pressures. Which of the following isotope will be observed a quick increase in the absorption volume initially at a very low relative pressure. So at lower relative pressure, you can observe very higher jump in the relative pressure and like the absorption volume. So at a very lower pressure, you can expect a higher absorption volume. So which is that kind of um, isotope? Is it type 1, is it type 2, is it type 3, is it type 5? Just think about that, sir. Just remember that graphs we discussed earlier and then try to answer this question. Is it a type 1, is it a type 2, is it type 3, or is it type 5? Just think it for a while and we'll take the answer. The question once again. Which of the following isotope will observe a decrease in the absorption volume initially at a lower relative pressures? Let me discuss the answer. Before I discuss the answer, let us go to the previous slide. Just see the answer from here also. So in which graph do you think there is a sudden increase in the absorption result? So a sudden increase can be observed and C. And this one. So in those two, there's a certain increase in the thing. So in the option A, it is given that, so the option it is given that it should be either type 1, type 2, type 3, or type 4. So you can see in type 2 and type 4, there's a sudden increase in the absorption volume related with respect to the relative pressure. And so the answer to this question is type 2 isotope. All right, go to the next question. So in dash and dash, so we can see how to do the answer. So dash and dash isotopes lack several niche. So the answer to this question is type 3 isotope and type 1. So actually should be type 1. So these two actually has this machine. Now hysteresis flow is wider for dash than dash. Which of that so generally there should be connection hysteresis flow. Try to think which one like the microphone, mesophone, or microphone, which one has a wider lobe than so on, say, very smaller lobe. So yeah, hysteresis lobe is going to be actually broad. Suction volume with spectroscopy pressure. So when you plot this, you can actually get a curve, something like this. So this is the width of the loop. So for which you have micro, so have macro. So which one has a wider loop than the other? So we just thinking for a while. But let's disconnect once again. The hysteresis will be wider for dash than dash. So the answer to this question is visa 4 and micro 4. So hysteresis flow for my visa 4 is greater than is wider than that of micro 4. Now let us move to the next question. Define the characteristics of the following hysteresis loop. So you're having four hysteresis loop A, B, C, and D. What are the basic characteristics that one can observe for these kinds of hysteresis loop? I'll give you a few seconds for you guys to think about the answer. Then I will remove the answer. Just think it for a while. Then I will remove the answer. I think you guys got enough time to think about the answer. So let us discuss the answer here. So the type A. So this corresponds to a cylindrical or tubular pore type, and it has a very narrow distribution of uniform pores. So this actually represents that kind of a pore distribution. Now let's go to the next question. It resembles the intricate structure of pores and is linked with link networks of form or the form of ink bonding. So here what happens is that there are multiple pores and these are interconnected to each other and it has formed a network within the material. So you can see for this kind of, so there is a cut happening here and this is very thinner, and you can see this is much more thinner area where this is much more a wider one, and you can see this is a very elongated one when compared to this, and this is kind of in a constant behavior where this is kind of a linear increasing. So these are the basically things that differentiate these two, and you can see this once more this area is more. So the area of this part for B is more for that of A, and this is kind of a constant, whereas this is an increasing motion. And actually, this length is much more larger than that of here. And yeah, this basically corresponds to the fact that the pores within the material is so in such a way that they are connected to each other and they have formed a network within this. And the type C suggests that the pores with capillaries processing larger diameter. So this kind of behavior indicates that the pores have a larger diameter, which is like pores have actually processed to become some capillaries, and these capillaries are having a very large diameter, which is greater than sorry 500 Armstrong. The last one mainly consists of a slit shaped pores into a process of micropore region. So it is having a slit-like process. Process would be something in the form of some cuts, in the shape of some cuts or slits, and the pores are in the range of micropore region. I hope you understand this. The type A is attributed to cylindrical tubular pores, and the type B is circular. It represents the networked pores, and type C represents two capillaries with diameter greater than 500 Armstrong, and type D consists of slit-shaped pores. I think we can go for the next question. And what is the basic equation for line bar isotopes? So this is a very common discussed question. So here, what is the basic equation for line bar isotope? Thank you for a while. And have a good answer. So the answer to this question is V by Vm is equal to theta, which is nothing but the product of K and P divided by 1 plus the product of K and P. With theta represent the fraction of volume absorbed by the molecule. V represent the volume of gas absorbed, and Vm corresponds to volume of gas absorbed at the minimal layer coverage. P represent the pressure of the gas, and K is a constant, which is the absorption. So basically, right now isotope connect the equations connect the variables V, Vm, K, and P. So it is of the form V by Vm is equal to Kp by 1 plus Kp, and which can V by Vm can also be represented as theta, which gives the fraction of fraction covered by the absorbed molecule. Yeah. So this is the Langmuir isotope equation. Now it's a match the following question. The one side it's type of isotope and the other side it's a type of adsorption. Think it for a while and I'll let you know the answer. The types of isotopes are Langmuir, Ferrantlich, Temkin, Borno, Emmet, and Taylor. And the type of absorption is chemisorption, multi-life physical absorption, chemisorption of absorption, chemisorption of absorption at low coverage. Think it for a while, and then let you know that. So this was exactly what Professor Tamal discussed in this story. So think it for a while. Yeah, let's check the question once again. It's a master following question. Is we need to match between the type of isotherm and types of absorption. The one side slime mode, friendly, Temkin, Browner, Emittella. The other side's type of absorption, which is chemisorption, multi-layer physical absorption, chemisorption, and physisorption. Chemisorption and physisorption at low coverage. Let's discuss the answer now. So the answer is one isotherm is basically mass between the chemisorption and physisorption. Currently, isotherm is basically is the isotherm which represent lower chemical and physical absorption at lower coverage. Temptin is basically just talks about this chemisorption and Rona emittent which is also known as PET, which is the very commonly used for absorption technique, is used in case of multi-layer physical absorption. So I hope you guys got this answer. Let's move on to the next question. In a tape plot, uh, we the x and y-axis are generally dashed. What are if you plot a tape plot, which is generally used to plot it for the thin film plot, thin film absorption. So what is the x and y-axis that are actually used? We give for a while, and then I will take the answer. Yeah, I think you guys got enough time to think about the answer. So the answer to this question is the volume absorbed versus the thickness. So the volume of nitrogen absorbed versus the statistical thickness of the absorbed layer on the non-porous surface at a corresponding relative pressure. So we fix the fix the pressure and then we calculate the statistical you calculate the volume absorbed as a function of film thickness. So for a non-porous material, the T plot has its y-intercept at 0, whereas for a microporous material, for a T plot, the intercept is have some value. So here you can see that the intercept is at 0, and here there's some specific value on the y corresponds to. So here there is second. So here you can see there is some value in y, which is a y-intercept, to be called prime, right? Which is a y-intercept. So this is the major difference that one can observe for a non-porous material as a microporous material. Okay. I think now we can move on to the next question. What are the basic stuffs in a surface measurement? Surface area measurement. Just surface area measurement. What are the basic steps that one need to follow when doing a surface area measurement? Think it for a while, and I'll let you know the answer. Yeah, now let me discuss the answer with you. The basic steps are: first step is the evacuation of the sample at a higher temperature, which is basically 1 milliliter to 50 degrees Celsius. Then the material is cooled to 77 Kelvin, which is the temperature of liquid nitrogen, in a container with complete liquid nitrogen. Then the partial pressure of nitrogen above the sample is gradually increased. The amount of nitrogen absorbed at each pressure. After that, we calculate the amount of nitrogen that is absorbed at each pressure. And at the time at which the equilibrium reached is also noticed. Okay, so I'll read you the steps once again. The first one is evacuation, which is also basically degassing. So we do the degassing at a higher temperature, which is 120 to 215 degrees Celsius, and then it is cooled to 77 Kelvin with a container of liquid nitrogen. Then the partial pressure of nitrogen above the sample is gradually increased. Then the amount of nitrogen, so it's actually 4 points. And the amount of nitrogen absorbed at each pressure after allowing equilibrium to reach is also noted. Okay, so I hope you got this answer. Let's move on to the next question. The downshift of dash state is smaller than the upshift of dash state. So just think it for a while, then I'll let you know the answer. So the answer to this question is both and dynamic. Downshift of the bonding state is smaller than the upshift of the antibonding. So how much does the bonding state comes lower is much smaller when compared to how much the antibonding state goes up. So yeah, I got this. I hope you got this answer. Now let's move on to the next question, which is in the figure A denotes dash. So here it's basically a plot which represent the potential energy ratios for the physics option process and the gas option process. So what is this A? What is this point A denotes? So what is the significance of this point A? So I can give you a few seconds for you to think about the answer, and I will tell you the answer. Okay, I think you got enough time to think of the answer. So the answer to this question is the point where A is the point where actually the physics option zone is actually left and chemistry option point actually sitting. This is the physics option. So physics option point comes like this, and at this particular point, it actually coins with the chemistry option zone. So yeah, this is the point at which if a solution can actually turn into a solution, and at above zero, you need to have some energy and dissociation energy to start this process. And below this zero, which you can see in this figure, it is a spontaneous process. Okay. So I think you guys were able to answer this question. Now let's move on to the next question. The A isobar represent dash with a lower heat of absorption than the isobar P. So what are these two quantities A and P? Identifying that this is a plot between temperature and the quantity that is absorbed. So yeah, just think of this. So initially the measurements that we made was isothermal, which means that the temperature was kept constant. Here the pressure is kept constant and the temperature is varied, and then the quantity of the quantity of the particles that is actually got absorbed on the surface is measured. So identify this A and B. So let us discuss the answer. So the answer to this question is physics option and chemistry. So the first A represent physics option and B represent chemistry option. So you can see from the figure, you can see from the figure that the physics option plot is much lower than the chemistry option plot. So this is A, which corresponds to physics option, and this is B, which corresponds to chemistry option. This is the quantity absorbed, and this is the temperature. Okay. So this we can round up today's class. So I'll be here for yet another 10 minutes. So if you have any doubts, please let me know. I can get your answers clear. So I'll be here for yet another 10 minutes. So yeah, go on, ask your questions, clear your doubts. I'll be here. So I hope you guys doesn't have any doubt or the doubts. So if you doesn't have any doubt, we will see in the next class. So if you have any doubts, kindly ask to me. So I'm stopping this meeting for today, and uh, we'll join for the next class in the next day. Thank you.